When we're naming alkenes with UPOC, we have to take several considerations into place. The first thing is we don't have an alkane with only one carbon, because in order for it to be an alkane, we have to have we have to have a double bond between two carbon atoms. Naturally, carbon only makes 4 bonds, so this means that the expanded form would be having 2 hydrogens attached to each carbon atom. When we further condense into a line angle formula, we draw this. We draw 2 lines on the same carbon-carbon connection to simulate that double bond, but what's floating around here are those 2 little hydrogen atoms that are showing up right there. So let's continue. This is my simplest alkene. The prefix for 2 is F, but we substitute ane for ene, which is the ending of alkene. So this is ethene. This is the UPOC name. Ethene is also called ethylene, which is its common name, and you might encounter it in many textbooks or web pages. The next alkane has 3 carbon atoms, 1, 2, 3, and we have a double bond between 2 of them. This is the same structure as its mirror image. So we have 3 different carbon atoms, and the prefix is prop, but instead of being ane, it's double bonding, propene. 3 carbon atoms. Propene also has a common name, it's propylene. And as we go forward, we will see a new feature developing when we talk about alkenes. So let's predict, what would be butene? Butene is 4 carbon atoms with 1 double bond. So I can draw this very simply. 1, 2, 3, 4, 1 carbon atom. However, this creates a different type of isomerism. If we do a positional isomer, that means that the functional group is going to jump places. Here we have the double bond between carbon 1 and carbon 2. So now I'm going to draw the bond between carbon 2 and carbon 3. So this is a different molecule altogether. Why? Because the double bond has jumped. But there's a third variation. Why? Because double bonds are not flexible. Remember, here, when we have a structure, there's a pi bond. And pi bonds do not rotate. So that means if I have things on the same side, they're never going to be on opposite sides of that double bond. So we have another shape, which is 1, 2, 3, 4 carbons with a double bond in the middle. Here, what we get is a very distinct shape. If I want to look at it like this one in the middle is kind of like a lightning bolt, while the other one that I have right here simulates kind of like a smile or a basket, okay? So this is a way to identify these features. Whenever you have carbons on the side that are on the same side of the double bond or on opposite sides of the double bond, this creates a different isomer. So in this case, we have 1 butene. Why 1? Because we're indicating that the double bond starts at the first carbon, so this is 1 butene. And this is how we start to get isomers in these alkene molecules. In this case, the double bond is at 2, but it also has a lightning shape. Lightning shape is called trans. So this is called trans 2-butene. And basket shapes are called cis 2-butene. In a sense, even though these have the same molecular formula, they're not structural isomers per se, they're called constitutional isomers. So that means that they have a completely different arrangement. Let's look at other examples. If I make a longer chain, I'm going to make several chains of 8, and we're going to analyze very quickly what goes on with this. I'm just going to draw my double bonds in different spots. Here, when I look at this chain, 1, 2, 3, 4, 5, 6, 7, 8, what do I have? First, I'm going to draw the position of my double bonds. 1, 2, 3, the beginning. And remember, for alkenes, the star of the show is the double bond. So that's the thing that we're going to include. That's the thing that we want to name and follow. At number 3, we have a double bond. And this molecule has 4, 5, 6, 7, 8 carbons. This one has 8 carbons as well, 8 carbons as well. So this is oct, ene, ending, but what are we missing? We're missing the position of the double bond, which is at number 3. But what shape is it? Let's look at it really quickly. This shape, if I take into account what's next to my double bond, it's clearly a lightning rod. So lightning rod, as we had said in the previous page, is trans. So this is trans 3-octene. Now I'm going to jump to the third example. We want to give our double bond the lowest number because it's the star of the show. So we want the longest chain giving the double bond the lowest number. Are we going to start on this side? No. We're going to start on this side so that we give the double bond a number 1. 1, 2, 3, 4, 5, 6, 7, 8. This is octene again, ending in ene. But the double bond starts at carbon number 1. Is this cis or trans? Some of you might say cis, some of you might say trans, but the answer is whenever the double bond is at the first carbon, it's neither cis nor trans. It's only the position of the double bond. So this does not have cis or trans. Let's look at the middle example. Again, following the longest chain, the double bond wants the lowest number, so I'm going to start numbering on this side. 1, 2, 3, 4, 5, 6, 7, 8. So, in conclusion, we look at this. This is also my lightning shape. This is the same molecule, it's just flipped on the other side. Just to make sure that you guys have it clear, let's draw another example. And this is where it matters how we draw our molecules. I'm going to draw it right here. And what happens with this? We're going to get lowest numbers for the double bond, so we're naturally going to start on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Very good. Now, 11 is on deck. We add ene to imply 11 carbons with one double bond. Where is that double bond? At number 3. But let's see what type of double bond we have right there. Is it a lightning rod? Can I draw a lightning rod? No, I can't draw the lightning. So it's a little basket, like I showed you on the previous example. It's like a C. Right? Here's the basket. And this means that this is a cis bond. Now, one last example. What happens when we have multiple double bonds? We're going to do that poly exercise. So, this is one type. I'm going to do another one right here with another type. And another one right here with a basket. 1, 2, 3, 4, 5, 6, 7. Again, lowest numbers for our double bonds. So I'm going to number this chain 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. If I started on this side, I would get number 2 and number 7 and number 6, so it wouldn't work. And same for this 1, 2, 3, 4, 5, 6, 7. What are these variations of? These are variations of hepta. Why hepta? 7 carbons. So I'm going to draw hepta. This is also hepta. Hepta. How many double bonds do we have? 1, 2. 1, 2. 1, 2. This shows up as di, splitting the carbon chain to indicate that we have 2 double bonds, heptadiene. So these are all variations of heptadiene, 7 carbons, 2 double bonds. Now we have to indicate where those double bonds are. Both of these double bonds are at the edge, so they're neither cis or trans. So we just add the locants at the beginning. 1, 6, heptadiene. For this one, however, the double bond at number 5 is trans. So we're going to write it first. Trans, what number? 5. And then comma, number 1. Heptadiene. And for this one, again, this is a cis bond. We're doing the basket shape right here. So this would be cis 4, comma 1, heptadiene. Basically, to recap, we're counting the number of carbons, 7, the number of double bonds, ene, diene, 2 double bonds, and where those double bonds are. But in this example, the addition is also the shape of those double bonds. It's cis or it's trans. In this case, number 5 is trans, and number 1 is a regular bond. In this case, cis is 4, and number 1 is regular, heptadiene.